Our next one, integration by parts. What it basically is the product rule, but rearranged for integration rather than differentiation. So when you have an integral which is the product of two functions then, but neither is the derivative of the other, so we can't set it up and go, oh look, it's derivative times function. It doesn't work. Then integration by parts is what we go and use. And the way I remember it, there's different ones you'll see, but I just simply remember it like this. The integral of u to v is uv minus the integral of v to u. And I said it's the product rule because if I move the integral of v to u to the left-hand side, then I'm saying, well, these two integrals added together is uv. If I differentiate both sides, then I get that the derivative is uv is u times the derivative of v plus v times the derivative of u. So it's your product rule, but we're using them for integration. Okay. How do I choose when I'm looking at it? So for u, what I try and do is I try and pick the function that when I differentiate it, it's going to be something simpler. All right? So if I've got a choice between two functions, because one's going to be times the other, I'm going to try and pick the one that's easier. The differentiation will make it simpler, sorry. And then the dv, because sometimes they might be equally as easy. So then I'll look at the dv. And dv has to be something that can be integrated, because I'll end up integrating the dv. All right, so let's have a look at this. Integral of x sine x. I've got two functions multiplied together. I've got x times sine x. I can't create the derivative of one in the other. So, all right, I'm going to look at it. So I said I'm going to choose u, which will make it simpler. Well, if I make u equal to x, when I differentiate that, I get 1. That's certainly simpler than x. If I chose sine x, when I differentiate that, I get cos x. So pretty much the same, really. It's just a trig function. So I'm going to choose u to be x. So du will be dx. My dv then is sine x. And so to get v, we integrate. And that's why dv had to be something that we could integrate. V, I get minus cos x. Okay. So the integral of u to v was u times v. So I've got minus x cos x minus the integral of v to u. But v is negative, so negative times negative becomes positive. I get the integral of cos x. And now I've got something a lot easier to work with. I can integrate cos x. Integrate cos, we get sine. And I've just moved the sign to the front because it's a positive and I think it just looks neater. So there we go. We get sine x minus x cos x plus, of course, a constant. Log x. Well, you might be looking at it and thinking, hang on, well, there's only one function there. There's actually two functions there. One of those functions is the number 1. So when we just have a function that we don't have a rule for, we can always use a product rule because we can say, oh, it's 1 times that function. So I've got to choose u so that when I differentiate it, it will be easier. Well, I suppose if I chose 1, differentiated, it gets 0. That's easier. Problem is, the other one has to be something I can integrate. So if I chose 1 to be that, then I'd say, oh, well, dv will be log x. So I just got to integrate log x. Oh, that was the question anyway. So in this case, I sort of got my hand forced a bit. So u will be log x. So du will be dx on x. So my dv is just dx. Integrate dx, I get x. So it'll be uv minus the integral of v to u. So u times v is x log x. Integral of v to u, well, the x cancels with the x, and I just get integral of dx. And that's something that's easy to integrate. X log x minus x. By the way, reality, if I get given the question, the integral of log x, I'm just writing down x log x minus x. It's another one of those ones that comes up a lot. Just integral log, and worth just, if you do remember it, it's fine to write it down. Same with any of these integrals. If you do happen to remember what the answer is, write it down. Unless they've actually said do it via a specific method, then obviously what they're testing then is, do you know how to use the method? But if that's not what they're testing, it's fine to just write the answer down because you happen. 0 to 1, xe to the minus 7x. Okay, u. If I differentiate x, I get 1. That's certainly simpler. What about e to the minus 7x? If I differentiate that, I get minus 7 e to the minus 7, pretty much the same thing. So it looks like I'm going to choose u to be x. So u is x, du is dx, so the dv becomes e to the minus 7x, integrate minus 1/7. So uv minus the integral of v du. So uv, notice it's a definite integral, so I've got my square brackets around what I've integrated. So the minus 1/7 x e to the minus 7x, going from 0 to 1, but now it becomes a plus, because minus times minus. A seventh, the integral e to the minus 7x. Now, whether you substitute in now, or you just wait until you've integrated the whole thing's up to you. I mean, the limits are the same, so it doesn't really matter. However you want to deal with it. What did I do? I waited. So if I integrate the second one there, I get minus 1 on 49 e to the minus 7x. Substitute in 1, substitute in 0. By the way, be really careful with exponentials when you're subbing in 0. It's so easy to go, oh, well, sub in 0, you get 0. But of course, e to the power of 0 is 1. It's not 0. And tidying that one up, there we go. There's an answer. Minus 8 on 49 e to the minus 7 plus 1 on 49. E to the x cos x. This is an interesting one. Okay, u. If I choose e to the x, differentiate it, I get e to the x. Yeah, all right. If I choose cos x, integrate it, I get, differentiate it, I get minus sin x. Yeah. Oh, well, maybe it's on what I can integrate. Integrate e to the x, I get e to the x. So I can integrate e to the x. Integrate cos x. Oh, I can do that too. Oh, so it doesn't really matter. I can choose whatever I like. I wonder which way I went. I went the e to the x for the u. So u is e to the x. So du is also e to the x. The v is cos x. V becomes sin x. Okay. uv minus the integral. I've ended up with an integral which is pretty much the same as what I started with, except it's now sine instead of cos. Oh well, gonna have to do it again. But here's the thing. Whichever way you went the first time, stick with it. Because if I was to now on this one go, oh, I'll make u equals sine x, and you'll end up like in a circular argument, and you'll end up with something like 0 equals 0 or something like that. So stick with your first choice. In this case, it was e to the x. So u is e to the x, du is e to the x, the v this time is sine x, v is minus cos x. All right. But it's minus all of uv minus v du. So it'll be minus uv, but that becomes plus e to the x, minus v du. Oh. Hang on. I'm back where I started from. But that's when I now look at this, and I don't think of this as working out. I think of it as an equation. What I'm actually saying is the integral of e to the x cos x is equal to this line. So I'm just going to move the e to the x cos x to the other side. So therefore, two lots of the integral of e to the x cos x must be e to the x sin x plus e to the x cos x. Divide both sides by 2, and there's my answer. Okay. So yes, you have your working out, but think about what your working out is saying. It's saying this line is equal to this line. So you can treat it like an equation if you need to, in this case, because it is a fact. Remember, we can move terms from side to side if we know with 100% certainty that it's true. And we know with 100% certainty that the integral of e to the x cos x does equal e to the x sin x plus e to the x cos x minus e. So I can move terms around to do that. I know, it feels like I haven't done any integration. Hang on. But I did, because we had to integrate to get the e to the x sin x and the e to the x cos x. There was integration there. All right, let's have a bit of a play with integration by parts.